So let's start. First of all, there will be, of course, problem about vectors. Vector algebra, it's impossible to do physics without knowing vector algebra. Physics 1, almost every class we're going to find components of vectors, magnitude, angles. And then in physics 2, exactly the same story. Right? So it's everywhere. So there will be problems about this. Then we're going to practice how to find components, how to add vectors. Then after this, we went into predicting future of the systems. And first, hello, more people. Yeah, move. First, we discussed what is called translational kinematics. First, we developed vocabulary, right? So basically terminology which we need to use in order to describe motion, translational motion. So we introduce position x, then if you differentiate it with respect to time, you'll get velocity, translational, and then if you differentiate velocity, you'll get translational acceleration. Again, it's banal stuff. Then that's how you can get them mathematically. Then graphically, if you have a graph, position versus time, and let's say blue is your graph, then how can you get information about the velocity? Just take a point where you want to know instantaneous velocity, draw a tangent line, and the slope of that tangent line is the value of the velocity. So slope, velocity, you can, by checking the slopes, you can plot, for example, velocity. Let's say velocity is this. Now, if you want to get acceleration, the same story, slope of the graph gives you acceleration. Here, slope positive, constant, constant. Here, slope negative, constant. So you get negative constant, right? So vocabulary of translational kinematics. And then we started predicting the future, right, of the system experiencing translational motion, and we derived equations, and they're only correct. They can be only used if your acceleration is constant. If acceleration is constant, it's illegal to use those equations. In that case, you will end up with a second order differential equation, which is the Newton's second law. That will be in the higher level courses. Yeah? All these formulas are there except for maybe finding components. But of course, I give you can look at the formula sheet. There is a triangle which tells you how to find sine, cosine, and tangent, how to find adjacent side, opposite side. So that is given. And of course, that's essentially what you need in order to find components. The rest, this is given. These are given. All this given. So prediction of the future, future of the velocity, future of position, and no time equation, which is sometimes very, very useful. Then we applied these formulas for the projectile motion. We have two-dimensional motion, so we applied these formulas twice for the x direction and for the y direction, motion in the y direction. Over here, of course, you remember we need to keep track of the pluses and minuses of the acceleration. If your y-axis is up, coordinate system, and acceleration due to gravity all the time is down, so in this case acceleration is negative. If you picked y-axis downward, then in this case acceleration is in the direction of the positive direction of y, so in this case acceleration is plus g. And of course, for this motion we assume that there is no air resistance, so there is no acceleration in the x direction, so as a result these equations are reduced only to this. Velocity, x component of the velocity stays the same, and this is the prediction of the x coordinate. And all these equations also can be written for the y motion, to describe motion in the y direction. Okay, so that's vocabulary and then prediction, future of the translational system. Now, after that, we went into the rotational kinematics, and exactly the same structure, exactly the same ingredients. Okay, not exactly, sorry, very, very similar, not exactly, similar. All right, so first vocabulary, like here. So motion, rotational motion, in order to describe it, we can use angle, right? And of course, we introduce angle in radians, which is arc length divided by the radius. Then, if you want to find how fast angle changes in time, we introduce angular velocity, d omega over dt derivative. If you want to know how fast angular velocity changes in time, you differentiate one more time in order to get angular, what is called the angular acceleration. Vocabulary, and then how to predict the future. Kinematic equations, extremely similar to what we have here. We just need to replace v with omega, acceleration with angular acceleration, and x position with angle. So that's it. So translational kinematics, rotational kinematics, and all pieces are very, very similar. So definitely there will be a problem on rotational kinematics. There will be problems definitely on translational kinematics, because you see you see the structure. We have vectors, translational kinematics, rotational kinematics, nothing else. Right? Again, tangential quantities, which we discussed just recently, are not going to be in the exam, because your homework is due, I think, right now, Friday. Because in my second section, 209, we just covered it just like a couple of hours ago. Right. Okay, so now let's start looking at the problems. So this is a quick overview. And, okay, I already took a picture of this. So first, let's practice finding components. So let me write, it's a problem number 1. I'm going to label them like this. So what if we have vector sum A, let me use capital, and its magnitude is given. Magnitude is 5, whatever units. Meters, kilometers, newtons, doesn't matter. And direction, 30 degrees above plus x. Oh, you know what? No, not plus x. No, it's not correct. Above horizontal line. Right. And I'm going to use different coordinate system, and we will try to find components of this vector. Very, very simple. So let's say this is my first coordinate system, y and x, and the vector, let me use red, 30 degrees above the horizon, so it's this. Okay, of course, which angle? Let's use conventional angle. You remember conventional angle from plus x-axis in the counterclockwise direction. So conventional angle is this. And in our case, it's given. It's 30 degrees. So finding components, I'm not even asking you, because it's trivial, right? So this will be the x component. And which function do we have to use in order to find the x component? Cosine or sine? Cosine? Yeah, adjacent side cosine function. Just remember it, right? So whatever mnemonic rules you use, just remember, right? So because it will be pretty much every class, in many, many classes, finding components. Right, and in physics 2 later on. So ax, it will be magnitude of a times cosine of 30 degrees. Then y component, yeah, so draw a normal line to the y-axis, and that will be your y component. Wait, it's not a straight line. So ay equals to a times sine 30 degrees. Okay, so then you remember very convenient vectors. We introduce very small vectors in order to define positive directions of coordinate system. You remember those name of those vectors? Unit vectors. You remember those unit vectors? I had positive x direction, j had positive y direction, and k had positive z direction. Let me just show them. So let's say this is our I hat, then this is j hat. Unit vectors, magnitude of 1. Right. Okay, and now in terms of these unit vectors, we can write this vector a as a equals to this ax times I hat plus ay times j hat. Okay, for whatever reasons, yeah. Good? I didn't plug numbers. Of course, you can plug numbers. Sine of 30 degrees, I know it's 1 over 2. 5 divided by 2, it will be 2.5. Right? So, of course, x component, cosine of 30 degrees is the square root of 3 over 2. Right? So I'll skip it. Okay. So that will be, let's say, part A. Now, part B. Let me turn my coordinate system by 30 degrees this way. So vector stays the same. Still, vector is the same in the this direction of the same value, but I will just turn coordinate system by 30 degrees. Whatever. I feel like it's, you remember, you have freedom to choose any coordinate system your soul desires. Absolute freedom. So I feel like, okay, for whatever reason, I want to change my coordinate system. I want to turn it. Okay, why not? So now a new coordinate system will be, and you know what, I will start with still drawing horizontal line because my vector is direction relative to the horizontal line for the sake of convenience. So my vector is still in the same direction, the same value, A. But now I'm going to turn my coordinate system, and which way? It's that way, yeah. So now my, let me use, yeah, still. So this will be my x-axis, right? So this angle 30 degrees, I just turn it by 30 degrees. So this is that angle 30 degrees, it's different, right? And y-axis is that. So now this is my coordinate system. Why not, right? So now let's find components of our vector relative to this coordinate system. Okay? So we just need to draw normal line, perpendicular lines from the end of the vector to our coordinate axis, to our axis. Right? So for the x component, it will be this. You see? Perpendicular to the x-axis or parallel to the y. And to find y component, we need to draw something like that. Soon, now we started discussing dynamics, we're going to do something like this, decomposing our vectors relative to coordinate system, which is somewhat tilted, inclined plane motion, right? So now, what will be, okay, now I will write underneath. So what will be the x component? Ax, of course it will be magnitude of A and times which function and which angle? Okay. 60? So we just need to see the angle between, you see, here we had angle between our vectors and the x-axis 30 degrees. Now vector here, and my axis you see tilted. What's the angle between this vector and our tilted axis? You see it's this 30 degrees plus this 30 degrees, it's overall 60 degrees, right? So we need to use now that angle, right? So, and since we want to find this side which is adjacent to this 60 degrees angle, so of course we need to use cosine function. Adjacent, cosine function. Opposite side, sine function. Again, use whatever rules, you need to remember that. Right? So A times cosine of 60 degrees. Okay, and now y component, of course, sine, right. And they're both in the positive direction, so everything is good. You see? All right, so A times sine of 60 degrees, right? And we can write again in this form, right? So the answer. So I also turn, okay, let me even look at one additional A, B, C. What if, still our vector in that direction, now what if I turn it that way? So still the same, this is horizontal line, our vector A at 30 degrees. But now I'm going to turn it in such a way that the angle between y-axis and the horizontal 45 degrees. So now I'm going to do it like this. 45 degrees. You know what? Let me even draw another dash line. So now this will be my you know what? No, what I don't like, my vector is a little bit, is almost also at 45 degrees. So that's why I feel uncomfortable, because now my x-axis will be almost on the, you know what, my angle is too big on the picture. So this is my A, so I just reduce the angle. Okay, and now x-axis will be like this, and y-axis like that. So, and this angle is 45 degrees. So we took this coordinate system and tilted by 45 degrees. You see? Why not? Again, there are plenty of situations where instead of using this coordinate system, it's more convenient to tilt it at a certain angle. Very, very common situation. All right, so now let's find components now of the same vector, but relative to this coordinate system. So again, the same. In order to find components, we need to draw a normal line from the end of the vector to each of the axes. So x, it will be this, right? And on the y-axis, you see I draw line perpendicular to the y-axis. And of course, this is our y component, right? So now let's find, okay, let me separate it. So it's belong to this, and this belong to that. Quick questions. What's the value of this angle? 45? Yeah, because you see we have essentially this line and this line. We have two lines, straight lines, intersecting each other. So essentially this angle and that angle are vertical angles. This and this angle are equal to each other as verticals. Right, so this is 45 degrees. And still, this angle is 30 degrees from the original statement, because vector A is at 30 degrees above the horizontal line. So now we have all the geometry that we need, and now let's write down x component and then y component. X component, which function and which angle? I also need to look carefully. Okay. Cosine 30, you're assuming that your x-axis, this one. But your x-axis, you see, it's this one. On purpose, I'm trying to twist your brain. Right? So you see x-axis, it's this. So essentially, what can you say about, for example, oh, you know what, maybe let's start with the y-axis. I mean y component. So it's at this. So you see, it's at this triangle, this point, that point. It's a right triangle. We know hypotenuse, which is 5, this, right? And we need to find this. So it will be magnitude of A times which function? Cosine or sine? Again, look at this triangle, this point, this point, this point. So this angle is what? 75 degrees, right? This is the angle between our y-axis and vector A. And we need to find side which is adjacent to this 75 degrees. So it's an adjacent side. It means function cosine, cosine function, and cosine of this total angle between the vector A and our that particular axis. So it's a cosine 75 degrees, right? Cosine 75 degrees. Okay, great. So now, what else? I'm ready to hear your screaming or what? You're smiling. Okay with that? No? You remember our in-class discussions, right? So what do we have to do in order to write the correct answer? Y component. Is it what? Yeah, yeah. Negative. Guys, you see, our vector points in somewhat in the negative y direction, positive y direction that way. So our y component, you see, it is in the negative y direction. And we're not using a conventional angle. You remember what's the conventional angle? Conventional angle, it's from positive x-axis in a counterclockwise direction. So conventional angle, strictly speaking, it's a way where it's so complicated. So from positive x-axis, it's a this, right, in a counterclockwise direction. So conventional angle should be, it's a this angle, which is of course scary angle. Right? So of course I would never use conventional angle for this problem. Or of course I would use convenient. Yeah, I would use convenient angle, which is of course in our case it's a 75 degrees. So since we use convenient angles, so pluses and minuses are not going to appear automatically if you take cosine or sine function of the angle, right? So you need to take care of that manually by looking at the picture. So you see y component is negative, put minus in front. Yeah, you want to say? 165 instead. Could we also use 165? Yeah, you can use different ways. 165, is it 165? Yeah, it's more than 165, right? So it's a 360 minus 75. It's a 315. Why would it be minus 75? No, would it be minus 15? Would it be minus 15? Okay, yeah, it's possible also. It's possible, yeah. But still, it's a convenient angle, yeah. Because cosine of minus 15 is not going to give you minus. It will give you still a positive value, right? So you have to manually adjust your answer. Okay, so yeah, it's minus. So be careful with, just look, what's the direction of the vector? Component, is it in the positive direction or negative direction, and adjust it. Great, so now x component. Okay, now of course x component everyone sees, right? So it's this side or this side. So it's essentially this angle is 75 degrees because this angle and that angle are the same, right? So it's a times sine of 75 degrees. And the component is in the positive x direction, so plus is great. Right. A times sine of 75 degrees. And of course, you can write it in this vector form using unit vectors I hat and j hat. Okay, good. It should be enough. So now, okay, any other questions? Yeah.
So for part B, how is the y component sine of 60?
Okay,
so
let's look. Let's look.
Is that angle equal?
Okay, I can say this way. This angle is 60 degrees, agree, right?
Correct.
So what about this angle?
Wouldn't it be 30? Why would it be 60?
Yeah, it's 60 degrees, the same like that. So essentially, you see one line and this line intersect two parallel lines. So this angle and that angle by geometry the same.
Okay.
Right.
Right.
So as a result, this side, it's a times sine of 60. Or this y component, it's this side.
Okay.
Right, so it's again a times now sine of that angle, 60 degrees, right? So, yeah. There are options how you can look at the picture. Good, so now let's look at multiple vectors. All right, so it will be problem number 2. And still it's a vector algebra essentially. Let's assume that there are 3 displacements of some car trip. So let me write, so we have a car trip which consists of 3 legs. All right, so leg 1, you know what, let me draw the picture. Let me draw the picture, it will be easier to see. So, so this is y-axis, just classic Cartesian coordinate system. And this is x-axis, right? And 3 displacements. First object moved in one direction, then moved in a different direction, turned and moved in completely different direction one more time. So let me show all these vectors. First, let me start with the blue, for example. So let's say this is my vector d. You know what? Let me give me my space. On purpose, I kind of displaced it from the x-axis, but essentially it's along x-axis. So displacement d1. The value of that displacement is 620 meters, right? Or miles. Yeah, meters. Then, next leg of this path, let's say it's this one, d2. Let me draw it here. d2 vector. And the value of that vector is 440 meters. In the last leg, now I will use probably black color. So the last leg is this. D3, the value of that leg is 550 meters. So 3 displacements. We need to find the total displacement. First, we will find components of total displacement, and then magnitude and direction. Oh, classic problem about vectors. So, total displacement, the net displacement of this. Yeah. So from the end of the first, from the beginning of the first vector till the end of the last vector, right? So just a classic way of finding, adding several vectors together. So this will be, which way I label it? D. Oh, just D. Okay. D sounds good. Right. So net displacement or total displacement. Let me call it D. Of course, it will be D1 in a vector form plus D2 plus D3. Whew. So now, ideological approach to solving this problem. I think we did it. Yeah, we did it in one of our classes, like 3 or 4 classes ago. Can we find components of this vector? It's a banal question, right? So of course, can easier. Then, the angles. I didn't give you the angles. Oh my God. So this angle is 30 degrees. Then this angle is 60 degrees. Let me draw this horizontal line. This angle is 60 degrees. And yeah, that's it. So it's enough. So now it's full. Then, since this angle is given, we should be able to find components of vector D2. Again, it's just a question of a few minutes of getting that. Then, components of vector D3. Again, it's additional a few minutes. It's like what we did over here. Except for the difference, here our vector was all the time, was at the origin. And now our vectors are displaced. Bigger deal, right? So it's the same situation. You remember, if you preserve the value and the direction of the vector, you can move it anywhere you want. For example, this vector D2 can be easily moved and positioned over here. It's still the same vector. It will still have the same components, right? Properties of vectors. Okay, so we can find components, and then how to find the components of the net vector. You just need to add corresponding x components in order to get components, x component of the net vector, then add y components, and then there is no z components. Two-dimensional situation. Right. Okay, so let's do it. First bullet, D1. You know what? I can write immediately the vector using vector unit vector notation. Right. So, of course, over here there will be x component, and then plus there will be y component. So, what's the y component of that vector D1? Y component. This is D1 vector, you see. So, what's the y component? Yeah, exactly. It's just pronounce it. There's no y component, right? It's 0, because the vector is in the pure in the x direction. So, a y component is 0. Of course, my vector looks a little bit ugly. I just try to displace it from the x-axis. As a result, it looks kind of weird. So y component is 0, and the x component then is the whole magnitude of the vector is in the x direction, 620. I will skip units, obviously meters. Okay, so the first vector. Now let's do the second vector. Now, of course, we need to find components. So D2x. D2x, so it's a D2 times which function? So you see, I want to find x component. It's essentially no, Pythagorean theorem, you don't need it. So we just need to find this x component, right? So Magnitude of this vector you see is given 440. Angle is 30 degrees. So we need to find that adjacent side adjacent to the given angle. So it's an adjacent cosine function, right? Cosine function, right? So yeah, it's like what we did over here, exactly this situation. Just our vector is displaced from the origin. And for some students, it's a little bit confusing at the very beginning. But again, remember, you can move vector anywhere you want if you preserve its magnitude and direction. You can take it home as long as it's in the same direction and the same magnitude. Right. So yes, it will be, and it's a positive component, you see, because that component is in the positive x direction. So it's 440 times cosine of 30 degrees. Wait, no way. I know cosine of 30 degrees is a square root of 3/2, but right. So it's 381 meters. Right. So then d2y, of course, it will be 440. Of course, now it's a sine of 30 degrees. And, oh, people, good, familiar faces. So what else? Y component. Yeah, anything else? Y component of this vector d2. You see, I wrote like this. Any suggestions? I see your hand. Any? Okay, I see. You? Any? Looks good. Good, good, good. No, he's he's unhappy. What? Negative. Now agree or not? Yeah. Now you're also unhappy, right? Yeah, of course negative. You see, y component of this green vector, it's essentially this. And you see it's in the negative y direction. And since we're not using conventional angle, we use convenient angle. So from cosine or sine function, the minus is not going to appear. So we need to take care of that manually. Right. We're trying to make our life a little bit easier. I don't like dealing with large angles, but as a result, you pay for that by losing some information, and you need to take care of that manually. So I will put minus. I should have left a little bit more space for that. Okay, sine of 30 degrees, I know it's 1/2. So it's a minus 220 meters. When I was a student, our professor, since we barely had any calculators at that time, so every time they used only angles, 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. As a result, I remember all those values by heart. So, yeah, and of course we can write d2 as 381 times I hat and minus 220 j hat. Okay, so that's our second vector. So let me even frame them slightly. Okay, this will be my first. This is the second. And now the last vector, d3. So let's find d3, d3x, and d3y. D3, it's a black one. So x, okay. X component of this vector d3. I'm ready to write. So of course it will be the magnitude. Let me even start writing. It's a 550 helping. And then which function? And you sure? Come on, you know that. I will never buy it. I know you. Look, yeah, I saw your hand. I see your hand. So x component, again, this vector, what is inconvenient because it is displaced from the origin. But the same rule. So you just draw a line, perpendicular line to the x-axis, right? And as a result, this is essentially your x component of that vector d3. Okay. In order to make it more convenient, I can take this vector and displace it over here. I can draw it. So this is my vector d3. This and that, it's the same. And now if I ask you, what's the x component? The same. You just draw this dashed line, and this will be your x component. And the angle, this 60 degrees angle, it's at this angle. Right? Of course, cosine of 60 degrees, and plus or minus. For x. Yeah, minus, because it's exactly the same. Right? Yeah, if you don't feel comfortable, just move this vector to the origin.
So 60 is like that.
60 between the horizontal line and the
Not for up to D2 is not 60.
No, for D2 it's a 30 degrees. This angle defines direction of that angle. And this is relative to the horizontal line. So this dashed line, which is now kind of covered by that component, it's relative to the horizontal line, so 60 degrees. Right. So, and a minus, of course it's a minus 550 cosine of 60 degrees. Cosine of 60 degrees, it's 1/2. So I remember that. So it will be negative 225. Wait, 275. Sorry, you didn't hear that. Right, negative 200. Yeah, what?
You're saying it's negative because it's in the.
It's an x.
I didn't see the negative over the 550. I'm sorry.
Yeah, minus. Yeah,
Yep.
yeah. Good. And the y component. Yeah, it's now I need to draw. Yeah, over here I can continue drawing. Right, so this will be our y component. And again, it will be negative. You see? You look confused. Good.
I think I'm following. Is it?
So I just this vector and that vector, it's the same vector. You can draw it anywhere you want. It's just more convenient for student very often to when the beginning of the vector at the origin.
So this one would be negative 550 times the sine of 60?
Yeah. Exactly. Right. So minus 550 times sine of 60 degrees. Sine of 60 degrees, square root of 3/2. It's too much for my brain, so I will look at my notes. Negative 476. Okay, so I can write right now vector d3 in a unit vector form. So it's just I hat times that plus j hat times that. So minus 275 I hat and plus minus 476 times j hat. So now the last ingredient for our salad, which now we'll try to create. So now we just need to add them. I mean, add the corresponding components. X component, x component, x component, y component plus y component plus y component. So that will be x and y components of the resultant vector. Right? Just simple rules of vector algebra. Right. So now d, it will be d1x plus d2x plus d3x in I hat direction. Adding just corresponding components, right? Everyone comfortable with this, right? So just simple, banal vector algebra, not even calculus. And the same with the y, d1y plus d2y plus d3y. It's so boring. That's we have notations of summation to reduce this amount of repetitive work. Okay, I will skip plugging numbers. I will just write down immediately the answer. Right? Yeah.
On the exam that you want us to write all that in, right?
No, you can skip some steps because you are limited in time, so you can skip this. You know, it's good to show what you do, because sometimes, yes, sometimes students find components, right? And immediately component of the final vector. Actually, I still want to see what you actually do, right? So yeah, I would prefer to see that you actually explanations that you're adding. Of course, explanations, it doesn't mean that you need to write a novel. Just write this. dx equals to this component plus this component plus this component. So I can follow your solution. Right, okay, so in my notes, of course, I plugged all the numbers. So now I will just write down immediately. Let me write underneath. D equals to 726 I hat minus 696 times j hat. Does it make sense? Positive x component, negative y component. Yeah, we see on the picture that our resultant vector is in the fourth quarter, right? So x component is positive, y component is negative. So this result seems reasonable, right? You look so confused, no? Okay, good. Okay, essentially, if you know components of the vector, you can say, yeah, problem is solved. But let's describe this vector in terms of magnitudes. Its magnitude, and direction. You remember like what we did in classes. So let's find the magnitude. Magnitude of D. Two vertical lines, it means the magnitude, right, the value. So how can we find magnitude? Yeah, I see your hand. Right. So how can we find magnitude? You do know. Everyone knows who sits here. No, come on. My students also very often ask you something, and no, we don't know. So, and then in a minute they realize, yeah, of course we knew it from the very beginning. Look, what we have. Let me draw another picture. This is my y-axis. This is my x-axis. And our vector D. We're now dealing with this red vector. You look so terrified. Okay, so this is our vector D, right? And what we found, this dx, it's an x component of the vector, and this is y component of the vector, right? So our x component, let me show on the picture. It's this side, it's dx. And y component, it's this dy. Okay, and now stare at the picture. We want to find the length of this vector, d. That's what magnitude is. And we found this dx, it's this number. And we found y component, it's this number. So you know this side, and you need to find that length. We need to use what? This point, this point, this point. We have this length, we know this length, we know this length, and we need to find the length of that longer one, hypotenuse. Say it. We need to apply the Pythagorean theorem. Of course, it's just banal Pythagorean theorem, right? Yeah, very often after all these manipulations, students think, wow, we're walking in some thick woods. No, it's just walking around three trees, right? Trying to get lost. Yeah, it's a banal Pythagorean theorem. So it's a dx squared plus dy squared. Right. Okay, you can plug numbers. I will skip it. I will just write down immediately the answer. 1005.7 meters. Whoa. What? Yeah, 1005. Of course, it makes sense to round it to 1006 meters, right? But again, on the exam, I don't subtract any points if you use slightly different number of sig figs. But of course, if problem gives you, I don't know, numbers with 2 or 3 sig figs, and the answer is 10 sig figs, of course, yeah, it looks a little bit too too creepy. Yeah, you want to say something? Yeah. Of course, any calculators, right? Programming, not programming, right? So anyway, you have all the formulas which you need, right? As long as you know how to apply them correctly, right? So I will be ecstatic at the end, right? Okay, and the final question. Let's describe direction of this vector D. Usually, for this situation, it makes sense to describe the direction relative to the positive x-axis, right? So let's introduce this angle phi and define direction of this vector by using that angle phi. So you can use any function, sine, cosine, but in this case, the classical way, of course, using tangent, right? Because originally we have these components, it's better to use tangent, right? But since we know magnitude, you can use any function you want. Right? So anyway, now let me write direction of D. So it's a tangent of phi equals. I just want to know the value of that angle. So I don't care if magnitude is negative or positive, I will just use an absolute value. Right. So it will be absolute value of the y component, because tangent of the angle, again, it's a right properties of right triangles, nothing else. You see, this point, it's a right triangle. Tangent of this angle, it's opposite side versus adjacent. By definition, that's how a tangent function we define essentially, right? So properties of right triangles. And in the formula sheet, there is a small triangle with angle is given, and what is tangent, what is sine, what is cosine is given. So if you doubt yourself, if you just look at the formula sheet, it's given. So opposite versus adjacent, magnitude of dx. And then, of course, we need to take arc tangent or inverse tangent. So phi will be equal to inverse tangent of 696 over 726. Right, 726, yeah. So if you plug numbers, I will just write down immediately the answer. 43.8 degrees. And I need to add what? To avoid any additional questions. If I leave my answer like this, most likely people will say, yeah, it's correct in the value, right?
Oh, degrees. Well, I did negative, but you just do.
Yeah, either negative, right? So, or what you wanted to say? Negative. I would just use below plus axis. Of course, yeah, it's a. But in this case, explanations are needed. Otherwise, it would be, if you provide a picture, it would be clearer, but not cool. Below plus x-axis. Okay, we exhausted this problem, so everything which is possible we found. And in Physics 2, we also start usually the semester with reviewing vector algebra. I usually give like 2 or 3 vectors, so I need to find the components, because at that time, again, students started getting rusty in terms of finding components. And okay, so if you don't have any questions now, okay, there's another problem, slightly easier. It will be in my notes. I will skip it. Now, let's practice a little bit displacement, distance, average velocity, and average speed. You remember the very first class which we had. You know what? I think I should be able to fit. This problem is not large. It's almost like a conceptual question. Or I think I even took it from the conceptual questions from the past. Okay, let me separate it like this. And I will call it problem number 3. And again, guys, at any moment, if something is not clear, let me know. So now hiker travels. Instead of car, now hiker. And let's describe her hike again with 3 displacement vectors. Yeah, so coordinate system. Since we're dealing with vectors, we have to show coordinate system. So first, this person travel, I will use blue, travel to the, okay, they use east, west, north, south, it's confusing. It's just to the left, and then up, and then to the right. So let's say this is the first leg, D1, and it's a 2-mile trip, 2 miles. Okay, maybe it's not the best. 2, let me. 2 miles. Then up 4 miles. D2, and it's a 4-mile leg. And then she came back to the y-axis, and that is running out of color. Okay, let me use black again. this way D.
Do you need a different marker?
No, you have pink. No, I have only 4. Yeah, I have also in the office some different markers, but it's probably in among all my purchases I've made over my teaching years, this is the best one. I cannot imagine even living without this, teaching without this, not living teaching. So D3, 2 miles. Again, obviously, because now D1 and D3 are the same in the value. Okay, so we need to find average velocity and average speed. And then average speed. So, average velocity. Actually, I didn't write on this review those formulas, but I'm sure that you remember. Average velocity connected with which quantity?
Displacement?
Displacement. Again, both vectors, right? So, displacement, of course, total displacement. Let me, yeah, it's a total displacement, obviously. Displacement divided by the travel time. You remember displacement? It's like a boss's attitude. I don't care about your actual trip, right? So you were here, you were supposed to be there in 5 hours, right? So if you went to get coffee or went to the bathroom, I don't give a whatever, right? So it's a boss's attitude. So this is the initial point, this is final point. Displacement is this way. It's, again, not a straight line. Again, to the best of my artistic skills. So that's our displacement. Let me call it D, total displacement, right? So, and you know what? I should have written displacement, and I let me put a vector sign on top of that. Of course, it's kind of clumsy notation, but yeah. And average velocity also as a vector. So displacement. What's the value of the displacement? Actually, not the value. Can you tell me as a vector? So what's the displacement?
0 I hat plus 4 j hat.
Okay, let's skip 0. Let's write immediately. So you see, the value of this displacement is 4 total. And direction in the positive y direction. So it's a j hat. So it's a 4 times j hat. Right. So it will be 4. Okay, I will skip units. 4 times j hat and divided by, I didn't give you the travel time. Silly me, 2.5 hours. So the travel time, okay, let me write, it's a hiker, and the travel time, 2.5 hours. Yeah, it's a decent hike. Right. So divided by 2.5, okay, now I feel like I still want to write miles and hours. So now we're getting the vector, and of course 4 over 2.5, it's a 1.6, 1.6 in a j hat direction, obviously. And units of miles per hour. Okay, makes sense, clear, right? Now let's talk about speed, average speed. So average speed connected to which quantity? Distance, of course, distance, yeah. Average speed, it's a scalar function, right? So speed also. Speed, it's the distance of an actual path. It's not like a mom who wants to know all the details of your trip, right? So not like boss, I don't give just initial point, final point. It's a really, really caring quantity. So it's a distance. Distance over the travel time. And so what's the value of the distance? Yeah. The value of the distance, you see? Yeah, 8. So 2 plus 4 plus 2, it's 8 miles. Total distance is 8 miles. So 8 miles divided by the same travel time, of course, 2.5. So if you divide it, you will get 3.2 miles per hour. So you see, value of the velocity and the value of the speed, of course, is different, right? So here 1.6 and here 3.2. Right? Okay, so I think it should be enough in order to refresh distance, displacement, average velocity, average speed, right, so on. Good, so now let's read graphs. That's where plenty of confusions, right? Let's read graphs and connect them with the physical situation. Okay. I see a red dot, it's recording. Oh, out of storage. Okay. I didn't realize, I need to clean the smartphone. Okay, let me erase this. So that will be problem number oh, it's difficult to erase this red. You know, after each exam review session, when you erase it and it's so hard, you feel like you need some physical therapy for arms. Okay, let me go into this as well. So, so it will be number 4 and translational motion. Okay, let's let's say reading graphs. And of course, it's a translational motion. Okay, so let's start with the position graph. And then, of course, we connect it with the physical situation. So the x versus time and the graph of this shape. Let me use blue. So first it starts here, then almost like a parabola. Of course, it's not a parabola, but and it should be symmetrical. Okay, good. And maybe I can say this is initial point is some x1, and this point x2. Right, and this is. So I want to describe physical situation, what actually happens. And then I want to plot velocity versus time and acceleration versus time. So this will be my later velocity. You know what, let me draw it like this, versus time. And then there will be acceleration versus time. Okay, let's start reading. So let's assume that my x-axis, you see it's a one-dimensional motion. There's only x. So let me introduce coordinate system. It's a x. Let's say this is some origin somewhere. Right. Okay, now. And it's some object moves. So it starts with some large value of x1. And then x starts getting smaller and smaller and smaller and smaller. So it means that it moves on our coordinate system to the left that way, right? X is getting smaller and smaller and smaller, right? So I can say that maybe, let me use, let me use red. So let's say this is my x1 somewhere, all right, so large, and then object starts moving smaller, moving to the left, x getting smaller. So it comes to x2, it stops for a moment, all right, and then what does it do later?
Turns around.
It's a turning point. So it comes to the minimum value of x, okay, according to the graph, this minimum. Stops for a moment, turns around, and x starts increasing. It means that it starts coming back. So let's assume that this is, for example, that point x2. So essentially, it moves this way, then stops for a moment, turns around, and comes back to essentially the same initial point. So it's a turning point situation. So you drive the car and you want to turn around. So you do something, come to the point, turns around, and start coming back. So it's I call it U-turn case. U-turn case. Actually, it's good. So it's a U-turn case or situation. U-turn. Okay, so now, we connected graph with the physical situation. Now let's plot velocity versus time. So what happens to the velocity?
Wouldn't it just be like a straight line diagonally up in terms of, because this is the rate of change of the...
Again, of course, we assume, since all our discussion usually about constant acceleration, so we're going to make that tacitly assumption that acceleration is constant, right? So we assume that first, of course, it was driving with some initial velocity, initial speed. And of course, in order to come to this stop, to the turning point, so you need to make your velocity, final velocity 0. So you are decelerating. So you press the gas, acceleration in the opposite direction, you still move forward, so you're preparing for a U-turn. So velocity first must be large, largest out of all. Then at this point, at this moment of time, let me say it, let's say some moment of time t, I can even maybe connect all these graphs with this dashed line so that all these graphs were linked. Right? So it means that at this point, velocity the largest. What else can you say about this velocity over this part of the trip? By looking at the graph or by looking at the physical situation. What else? First, again, it's larger and then becomes 0. What else can you say about that particular velocity?
So that means it's decelerating.
Decelerating, still great, but still, what else can we say about that velocity?
It's going in the negative direction.
Negative, so it means what? Velocity is? Negative. It's a one-dimensional vector. One-dimensional vector. Is that what you wanted to say? Yeah, of course, it's negative. So it means that it starts with the large negative velocity, which becomes less and less and less negative. And eventually it will be 0. So it means that it will be straight line, but it starts somewhere maybe, okay, over here. So it comes to this point, right? So it's a first. Actually, this line, no, I don't like this line, because it's a graph. Right? Agree?
Yeah.
So then it's a 0 velocity at that particular moment of time. And actually also, why is it negative? Because you see the slope at this part of the graph is negative everywhere. You can look at the slope, it's negative, negative, negative. Velocity is negative. So now this part of the graph, slope now is positive. At this moment of time, it's 0, and then slope gets larger and larger and larger. Velocity is getting larger and larger and larger back, right? So it recovers the velocity. Great. So it means that it will continue this way. So you're absolutely correct. It is a straight line, but of course with yeah, what the difference? All right. So it's a turning point, and you remember in our second class we discussed what's the major feature of the turning point, kind of like a test which you need to run.
Velocity 0.
No, not 0. Velocity 0, it can be like this. I'm moving this way, stops, my velocity 0, and then I'll continue moving. It's not a turning point, right? No, 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 no. About velocity is correct, but not completely correct. So what happens to the velocity at the turning point? Change the signs. You see here, velocity negative, then velocity positive. Okay, if this is my positive x-axis, first I move in the positive x direction, turning, now it's negative. Or if this is my positive x-axis, so now I'm moving in the negative, and then I'm moving in the positive every time, change in the sign of the velocity, right? So, yeah. So it's a turning point. All right, so let me even say this is a turning point. Actually, I wrote it's a U-turn case turning point, so it's clear. Great, so now acceleration. Yeah.
I'm a bit confused on the velocity graph because doesn't that say that your velocity starts negative, so you start by going backwards?
No, 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 no. Negative velocity, it's a vector. It just tells us it points in the negative your chosen x direction. That's the only meaning. So if we picked x-axis that way, so negative, it means that the object moves in the negative x direction. Negative vector, it has only one meaning. It's a negative x direction or negative y direction. Yeah. Or plus or minus vectors, it has only one meaning, direction, relative to the positive x, well, y. Great. And acceleration. Over here, acceleration. What can we say? Okay, it's constant, right? Because acceleration, it's a slope. Like over here, it's a slope. And slope, positive, negative? Positive, right? Slope, positive, and slope exactly the same over here and over there. So acceleration is that constant, right? And positive, which is actually interesting. So let me draw it first, and then we will discuss. So, since initial is over here, so, and this. So this is our acceleration. Which is strange because, look, here you move that way, and here you move this way, and acceleration is positive for both cases. How come? So let's just look. Huh?
Makes sense.
Makes sense. No, look what I mean. Here you move this way, and you decelerate. So acceleration is that way, in a positive x direction, right? Velocity this way, and you decelerate, so acceleration that way. When you turn around, now velocity this way, and you accelerate, so acceleration still in the same direction. So deceleration, acceleration that way, acceleration, acceleration, and acceleration that way, right? So interesting case. It's acceleration, it's not velocity. Sorry. Okay, makes sense? Now let's look at another situation. In the last situation I will skip. So let me call it case A, now case B. So again, information about the position is given. X. And now graph looks like this. It starts, let's say, somewhere at x1, then it goes up, and then almost like a tangent function, but displaced from the origin, something like this. Maybe I need to increase my x-axis. Yeah. Okay, so let's start discussing. Again, we assume that x-axis in the that way. Let's say this is x1, then this, I think x2 I label it. Yeah, let's label it as x2. So let's start reading. So it starts at x1, which is small and positive. So if my origin, for example, here, so it starts somewhere, let's say here. This is x1. Right? And x increases. So it means that it travels in a positive x direction. So it starts here and travels this way. Then it comes to this point. What can you say about the velocity at that point? Slope, and what's the value of the slope? 0. Yeah, of course, 0, right? So it comes to a stop, complete stop. Maybe it's let's call it point x3. So it will be over here somewhere x3. So it stops for a moment, and then what it does after that? Keeps moving. It's basically what I just a few minutes ago I tried to demonstrate. So essentially, it looks like it starts here, moves in the positive x direction, stops for a moment, and continued moving in the same direction. I decided to call it like a red traffic light situation. But of course, you stop for just for a moment, right? And you keep moving in the same direction. So it comes to here, stops, and then continued moving to point x2. Right. So how did I label it? Red traffic light case. Right. So it's a red traffic light case. Okay, so now let's look at the velocity, details of the velocity. So velocity versus time. And so first, what happens to the velocity? Positive. And first slope is large, so velocity is large, and then velocity getting smaller and smaller and smaller and smaller and becomes 0. And positive all the time. So it means that it starts with the large value and then gets to 0. So it means that I use red. So let's say this is our maximum. And again, we assume acceleration is constant, following our traditions. And again, let me connect all these graphs with this dashed line in terms of time. So it means that it starts here and linearly comes to this point. At this moment, object stops for a moment and velocity is 0. After that, still slope is positive, velocity is positive, so the graph will come back, bounce back to the first quarter. And first velocity is small and they're getting larger and larger and larger, and it's back to essentially the same as there was an original one. So essentially we will have this V-shaped graph. Right, V-shaped graph. And final acceleration. Now let me draw t-axis over here. So acceleration is constant. Here acceleration is negative. Here acceleration is positive. And the same in absolute value. So we're going to have a step function. Yeah?
Wouldn't the velocity graph look more like a parabola instead of like a V-shape?
No, I assume that our acceleration is constant. So it will be a straight line. Right? Of course, it's difficult to see that it's a straight line by looking at this graph. It's difficult to draw a graph which will give me a straight line. Sorry. Beyond my artistic skills. Right? So now, yeah, I need to extend this line. Right. And so here it's positive. So something like this. And then it will be drop to exactly the same value but negative. So now it's a step function. Here we have just a, I use green, but okay, good. So this is acceleration. Yeah. Acceleration is the slope of this graph, velocity versus time. So here slope is negative, graph is going down, right? And here, okay, sorry. Good point. So wrong face. So negative, so it's here, and then positive, it's there. I will have to do editing in the video. No, I will keep it all. It's too much work editing. Right. Yeah.
And so you would only draw those two lines because the middle is the stop, so there's no acceleration in that moment of time.
Yeah, that stop, that point. Yeah, in terms of derivative, you know what? It's a complicated point to discuss a derivative of that when you have two straight lines intersecting each other. So just something happens, and we have a step function from here to there. So yeah, derivative of the function which behaves like this is tricky business. Okay, so now let's read more a little bit of graphs. Now free fall. Where is my ball? Oh yeah, it's here. So I will draw you a few graphs, and we will try to understand to which situation that graph corresponds. Throwing up, throwing down, right? So like that. So it will be now problem 5. Let me separate it like this. And so now we have a freely falling object. You will understand in 10 minutes why I put in the quotes like a freely falling object. And let's assume y-axis is up. Yeah, assume y-axis is upward. So, part A, first graph. Let me draw something simple, reasonably simple to warm up. It's been a long day. Y versus, not y, velocity versus time, not position, sorry. Velocity versus time, and velocity behaves like this. Right. And again, let me show you immediately that the y-axis is up. So here somewhere there is a ground, 0. So this velocity graph corresponds to which situation? So what do we do to the ball in the field of gravity? Just drop it. Throwing up. Just dropping. Y-axis, you see, it's that way. Acceleration due to gravity, of course, straight down. Right. So let's start reading. So for this coordinate system, so v is positive. So it means that object moves in which direction, up or down? Up. In the first part, in this part, you see this part of the, over this period of time, velocity is positive, positive, positive. It means that object moves up. So it's definitely not dropping situation, at least not at the very beginning, right? So y-axis is up, and velocity is positive. Positive vector, it means it points in the positive y direction. Right? So it means that first object, let me use blue, moves, okay, this is my object, moves up. And it decelerates. You see velocity is getting smaller and smaller and smaller and smaller linearly. So constant acceleration due to gravity, right? Decelerates it. So, and then it comes to this point. It stops for a moment. So it comes to a certain height, stops for a moment, and then what happens to the velocity? Becomes negative. You see, now velocity is negative. Negative velocity, it means it points in the negative y direction. So now it's a turning point, and now object moves. The ball, whatever, started moving down, accelerating. So on the way up, velocity was getting smaller and smaller and smaller. It was decelerating naturally, right? And then turns around, and now it moves back, accelerating. Right. So essentially, it's this physical situation. It's a turning point. Essentially, it's this, but now in a vertical direction. Here we were decelerating maybe with the, and accelerating with the brake and the gas, and now it's only under the influence of gravitational, force of gravity, right? So it's a, how I call it, a ball thrown up, right? So it's this situation. So it's this case. You know what, now let me go out of order. Okay, this is clear. Now I will not following my notes. Now part B, let me discuss this situation. So again, velocity versus time. And now we have this crazy looking function. So first it goes down, then it jumps and goes down again. So let's start reading. Again, still the same coordinate system. Y-axis is up. Let me redraw it over here somewhere. So it's still y-axis. This is the ground. This is 0. So let's do the same. First, velocity is 0. So then velocity starts increasing, and it's negative. Negative velocity, it means it moves down in the negative y direction. And initial velocity is 0. So essentially, what did we do with the ball? We just dropped it, right? So first part, from this point to that point, object, here. From this point to that point, velocity is negative. It means it moves downward and accelerating. So it means that the ball was here and it moved down. Then what happens? Actually, now you understand why I put this quotes, freely falling object. So essentially now something happens and velocity jumps from the positive, from the negative to the positive of the same value. So most likely, what's the physical situation? So and now velocity is large immediately and positive, and then it starts getting smaller and smaller and smaller. So revelation. Yeah, it's essentially this situation. Ball was falling down, then collided with the floor, and then bounced back. Of course, we did not discuss interactions, collisions, right? So, but we're discussing only the motion part. That's why we don't know what happens over here. It just suddenly bounce to the positive value, right? It's a bouncing situation. But you release the object because initial velocity is 0, so essentially you released it, right? Yeah, so it's a ball bounces off the floor. So bounces off the floor. Okay, in the last some weird example, let me look, because there are like 5, it's too much. So which, some creepy one. Okay, let me look at this case. So it will be C. And now let's say we have this graph. So V versus T, and the graph like this triangular. Again, you will have to turn on your imagination. So first part, does it look familiar? It's the previous case. You see? It's this part. So essentially, in the first part, you drop the ball. It starts from 0, negative velocity, so it means in the negative y direction. A velocity keeps increasing, increasing, increasing in absolute value, reaches maximum, and then what happens then? Again, turn on your imagination what might happen. So for whatever reason, now velocity velocity still negative, but it's becoming smaller and smaller and smaller. I can give you two explanations, for example, and again, that's why I put a quote. So you drop the ball.
Maybe it's in water.
Yeah, that was my first way of explaining this situation. I remember in the previous time when I taught this course. Yeah, essentially, imagine that instead of flow, you have water. You release the ball, it hits this point, and then because of the buoyant force, of course, a velocity starts getting smaller and smaller, and eventually it will stop. Or yesterday, preparing for this class, I gave another explanation. Parachute, for example. So you drop the ball, it speeds up, accelerates, right? So first, and then parachute gets released, and of course it will be still falling down, but close enough, right? So yeah, it's just some, just for fun, right? Explanation. Okay, makes sense? So I can draw another graph over here. So it's a velocity. So first, it travels. It's over this. It's a free fall. Released, free fall, and then parachute. Yeah. Okay, let me put a smile. Right. Okay, enough of these graphs. So now let's start solving problems, because there are plenty of problems with reading graphs, so that's why I spend so much of time reviewing that. Right. So now let's solve problem about kinematic equations. Then basically one problem on translational kinematic equations, projectile motion, and then rotational kinematic equations. Right. And of course, there are more situations of this type. You can look at my notes when I scan them and send them to you. So now I will need more space and bigger picture to solve problems about the projectile motion. So it will be number 6. Actually, it's not the longest exam review session. My sort of personal record when I teach physics 2, 1 year final exam, it took us 4.5 hours to complete. Yeah. It was Friday evening, lots of material. Right. Huh?
Physics 2?
Physics 2, right. Yeah, final exam, it takes close to 4 hours, usually 3.5. Usually after this exam review sessions, I feel really exhausted. All right, okay, so now tennis player hits the ball at a small angle. And initial velocity given, angle is given, and somewhere at a certain distance, given distance, there is a net 1 meter high. So we will have to find components of the velocity, and then we need to find the moment of time when it will reach the net, and also we need to answer the question, is it going to clear the net? And then, of course, final velocity we're going to find. So there will be like 6 questions close to that. So you know what? I will need more space than this. And I forgot which problem is this. I think it's a number 6. All right. So if I miscount it, it's fine. So tennis player. So let me draw coordinate system immediately. Let me introduce. And of course, x-axis will be along horizontal line. And the tennis player hits the ball 2 meters above the ground. yeah, it makes sense somewhere. This no, 2 meters. Yeah, it's over here somewhere. So let me draw. So y-axis, x-axis, then tennis player. The initial position of the ball will be somewhere here, right? So it's a tennis player here, and the racket hits the ball. All right, so it will travel. Let me draw trajectory. It's useful. Right? So of course it will go first up, up, and then it will go down. And every time I don't have my x-axis is not long enough. All right. So now net somewhere over here. There is a net. So it's a net, 1 meter high. H equals to 1 meter. And now, yeah, this distance is 2 meters. And initial velocity is given. Value of the initial velocity is 20 meters per second. V naught equals to 20 meters per second. So initial height, initial velocity, and the size of the net. Horizontal distance to the net is given. Okay, yeah, I remember there was something else. So this distance is 7 meters, which makes sense, right? So you know the distance from where you serve to the net, roughly. Right? So now let's write down everything which is given in terms of coordinates, so that it will be very, very useful. So let's start with x over here, and then over here there will be y ingredients. So acceleration in the x direction, you remember 0. We assume that there is no air resistance, 0. Acceleration in the y direction, positive, negative acceleration in the y direction. Acceleration due to gravity is 0. Oh, sorry. Straight down all the time, g, right? Okay, you, yeah.
So is the height of the tennis player 0 or
2 meters. So acceleration for our equation due to gravity will be positive or negative for the equations? No. You're guessing. Look at the picture. All right, positive and negative. It's a vector. Only one meaning, like we discussed. I forgot with whom. If vector is positive, it means it points in the positive x or y direction. Negative, it points in the negative x and y direction. It's the only meaning. So yeah, now you're thinking. So you see acceleration due to gravity straight down all the time. Which direction relative to the chosen y-axis? Down, negative. So g, acceleration due to gravity all the time downward. We cannot change that. We are not gods, right, to change the nature. But if I pick y-axis upward, so it means that the acceleration due to gravity is negative. If I picked my coordinate system y-axis downward, then the g would be positive. But since I picked it that way, I feel it's more convenient to use that coordinate system. So it's negative. You see, this vector is down, but the y-axis is up. So it's a negative vector. All right. So it's a minus g. Then positions, x naught, initial position of the ball, it's the origin. Yeah, it's at 0.
So the acceleration, you're taking the acceleration of the vector going up.
No. We have two independent motions. In the x direction and y direction, of course, they are connected. They're kind of together, but mathematically they're independent. So right now, you see, I'm writing only information about what happens to the ball, to the y components of the ball. Right. So acceleration, a y component of the acceleration. So acceleration due to gravity, there's only one in the y direction. 9.8, it's all, we all know that, right? So now we just need to, for our equations, for these equations, like over here, you see I wrote this, right? So we just need to find the correct sign. So if you pick y-axis upward and acceleration due to gravity down all the time. It's all the time. So you drop the ball, it accelerates with 9.8. If I throw it up, it decelerates with 9.8 meters per square seconds. All the time 9.8. The question is it positive or negative? Relative to our chosen coordinate system. I choose coordinate system, y-axis. It's this situation. Y-axis is up, but g is down all the time. So relative to this positive direction, it's negative. Right? If I picked my y-axis downward, I have a freedom to choose any coordinate system I want. But I feel like for this problem, this is more convenient. But if you picked y-axis downward, then acceleration will be positive plus g, plus 9.8. Okay, so initial position for the ball, x naught is 0 because it's at the origin. Y naught, it's your number which you ask me to clarify. Of course, 2 meters. Of course, 2 meters, right? Then, initial velocity, let's find immediately. It's actually part A of the problem, find components of the initial velocity. So, v naught x, it will be. So, x component, again, decomposition like what we did at the very beginning of this exam review session, finding x and y components. Now it's the same situation. And again, you see, vector is displaced from the origin. So, but anyway, so now it shouldn't be a problem. So this will be my x component of that vector, v naught x, and this will be my y component, v naught y. And the angle I told, but I didn't write and I didn't show what's the value of the angle. 5 degrees. Well, it makes sense. Nice serve, right? So the angle is small between the horizontal line and the ball. 5 degrees angle seems reasonable. So, of course, I'm not asking. So it's a v naught times cosine of this angle because we need to find the side adjacent to the given angle. So v naught times cosine of 5 degrees. Right. Again, v naught is given, 20 meters per second. Cosine of 5 degrees, of course, no way. I will just look at my notes. 20 meters per second times cosine of 5 degrees. So it will be equal to 19.92. I keep more sig figs because it's not the final result. We're going to use these results later, so it's better to keep some extra sig fig. Right. Okay, so let me separate these 2 columns with these 2 lines. And now let's do the same with the y component of the initial velocity. So of course it will be now sine of 5 degrees. I will write immediately the answer. 1.74 meters. Oh, meters per second. Sorry, meters per second. Right. Okay, so I think now we have everything that we need. Equations are over here. I don't want to rewrite them. So now let's start answering questions. And this is x-axis. And let me separate. And part A, it was finding these components. So part B. So we need to find the time it takes for the ball to reach the net. So essentially, we need to find the travel time from this point to this point. You will understand in the next part of the problem why we need to know that time. So we need to find this travel time. So let me call it, I don't know, T1. So we need to find T1 to reach the net. Okay, not to reach the net, to reach x component of the net. Right, to reach x component of the net. Because we don't know if it's going to reach it, is it going to clear it or not, right? So x component of the net. Okay, so you remember our previous classes discussion, what determines the travel time? Now you remember in our discussions every time when the ball was hitting the floor, so the coordinate of the floor determined the travel time. But now, essentially, coordinate of the x coordinate of the net determines the travel time. right? So it means that we need to use which equation? Only one. There is only one for the x, right? So it's this x equals x naught. So there is only one equation which can be used, right? So look, x, it's 7 meters. I didn't write. So you know what? Let's add that information to this table. So let me call this x1, since it's a t1, x1, 7 meters. X1 equals to 7 meters. It's a given piece of information which it's good to add. So this is given, initial is 0, initial velocity, x component of the initial velocity is given, so we can find travel time like that easily. Right? Okay. So x1 equals to x naught plus v naught x times t1. Again, this is 0, and so from here we can easily find t1 equals to x1 divided by v naught x. Right. It's just one equation and the answer immediately. 7 meters divided by, where is my x component? 19.92. So t1 will be equal, of course I will look at my notes, 0.351 seconds. 0.351 seconds. Yeah, it's strong surf, short time to reach the net. So now we need to answer the question, does the ball clear the net? Now part C. Does it clear the net? So now, essentially, which piece of information we need to find in order to answer that question? Which quantity we need to find to answer that question? Okay.
Y1.
Y1? Yeah. Why not? Y1. Right. So yeah, essentially we just need to find this distance, essentially, which is y1 coordinate, right? Coordinate of that point, y coordinate of that point. Yeah. So we essentially we need to find y1. Right. So which equation is better to use? Y is in this equation and that equation. So since we have a travel time to y1, right? So it looks like this equation will be better, right? So this is what we need to find. This is 2. This is given. Yeah. Which equation did I use? Yeah, of course that one. Yeah. So y1 equals to y naught plus v naught y times t1. And acceleration due to gravity is negative. Acceleration due to gravity is negative, minus. So over here, there must be minus 1 over 2 gt squared. So it's minus 1 over 2 gt1 squared. So why not? Oh, it's not 0, sorry. Actually, nothing is 0. No, it's depressing. Right. So y naught is 2 meters. Initial velocity y component, it's very small, 174 meters per second times 0.351 second and minus 1 over 2, 9.8. I will skip units. And the travel time, 3.351 squared. So I just plug numbers. Okay, if you calculate, you will get, actually a nice number at the very end. So y1 equals to 2 meters. I should have written 2.0, it's fine. Right. So yes, it clears the ball. Oh, the net, sorry, it clears the net. So it means that this gap between the ball and the net is still 1 meter, right? So the gap equals to 2 meters minus 1 meter, so it will be 1 meter. So that's the distance between the ball and the net at that particular, yeah, at 1 meter. Okay, so now let's find final velocity at this moment, at this point. Let me call it point 3. So this point 1 or point 2, since I already, yeah, let me call it point 2. And my x-axis is in my way. So part D, so let's find V2. Magnitude. Let's find magnitude at that final point. So in order to find magnitude, we need to find first components, right? X component, Y component, no way out. So first we need to find components. And let me draw it on the picture. Again, it must be tangent. So velocity will be somewhat like this. It's our V2, magnitude of which we want to find. And of course the X component, it will be this V2X, and this will be our V2Y. Right. And then if we know components, of course we can find magnitude using, I forgot who, yeah, I was bugging you, right? So using that, I erased that. It was Pythagorean theorem. It's exactly the same situation we had before, just a different quantities. Quantities. I'm getting tired more. Okay, so let's start with the X component. So, do we know the X component of the velocity at the final point, at point 2? Or do we need to do some, or do we have to do some, make some funky moves in order to find? You see, V2X, it's this. We know what? Ooh, No, it's not 0, it's not 0. Velocity over here, it's not 0, because if I take this ball and throw it, and you'll try to grab it, so do you feel it's 0? Of course, it will be a velocity in the x direction, and of course, there will be velocity in the y direction, right? So again, some students think that when we talk about this final velocity, they think it's at the moment when it collided with the floor. No, we're discussing only flight, only the motion. Basically, this velocity, it's the velocity just before it collides with the floor. So, and at that moment, velocity is not 0, right? So, no, it's easier, look, you remember, okay, here's the key point.
So it's V initial,
Yeah, of course, x component of the velocity, exactly the same throughout the whole motion, because acceleration in the x direction is 0. Acceleration is 0, and x component stays the same. It's a very, the easiest part. So in this case, we don't need to do anything. We already found it. So this v naught x, it's the velocity throughout the whole motion. It doesn't matter. You take this point, this point, this point, this point, x component of the velocity exactly the same. Again, assuming that air resistance is small. Okay, so it is equal to v naught x and equals to what? 19.92 meters per second. Yeah, so it's easier part. Now, y component. Okay, now we need to sweat a little bit. We need to find it. V2y. So your suggestion, which equation? The third? Okay, I don't remember. I just need to look. The third equation. Actually, I tend to agree with you because we don't have information about the travel time to that point, right? And the question is not about time. So it sounds like equation, no time equation would be the most convenient, right? So let's see. That's what we need to find. This is given. We found g is given. Y, it's a final. It's 0, 0. And y naught, it's a 2. Yeah, so yeah, it's great. So no time equation. So vy squared equals to v naught y squared. Minus, because acceleration is negative, minus 2g and y2 minus y naught. And of course y2 is 0 because it hits the ground. Okay, yeah. All right, so vy will be equal to square root, vy naught, it's here, 1.74 meters per second squared minus 9.8, and minus, because of that, this minus, and minus 2 meters. So we can crunch these numbers. It will be 6.498. Oh, 6.498. Okay, of course it's a 6.5 approximately, 6.5 meters per second. Give or take. I just plug numbers. 1.74. It's this value. You see, initial y component of the initial velocity. Scientific discussion? Debating with each other? What, clear? Cleared? Okay, good. Again, you can ask me if something. Yeah, my handwriting is getting a little bit. In the final step, magnitude. So now, say it. Like, again, I'm asking the same question. That's why because I remember I was struggling previous time. So look at the picture. What we found, this is the x component, so we know this value. We found y component. Okay, it should be v2, right, v2y. So we found y component, and we need to find the magnitude of this vector. Of course, Pythagorean theorem. That's why I ask you again, because you remember. Yeah, just nothing fancy. It's Pythagorean theorem. So v2 equals to square root of v2x squared plus 2y squared. Okay, I'm not going to plug numbers. I will write immediately the answer. 20.95 meters per second. Okay, approximately 21. Okay, yeah, so that's the problem. And bonus question, let me ask you. Of course, I don't have any bonus questions and don't practice that. What if I ask about this maximum point, about the value of the velocity at that point, magnitude of the velocity, magnitude of the total velocity? Tricky question. No, I'm kidding, of course. So, magnitude of that velocity, what can you say? If you struggle, not struggle, but thinking, so let's start looking at the components.
Where would the vector be facing?
True. You're just delaying the answering the question with some fancy terms. Okay, what can you say about the y component of the velocity at the top point, at the maximum point? Y component.
It's centered. It's in the middle.
No, it's a trajectory, right? No, y component of the velocity at the maximum point, even one-dimensional motion. What's the y component of the velocity?
0.
You mean more confident? Yeah, of course. You see, in the y direction, stand over here and look behind this guy. So object moves from this point to the maximum point. It stops for a moment, and then it starts coming down to the floor. So y component of the velocity at the maximum point is 0 all the time. You just need to, I don't know, engrave it in your heart. All right, but what about x component of the velocity? Tangent, and the value, as we discussed over here, with you we discussed, right? So x component of the velocity at this point, it's still the same v naught x. like over there, like here. So throughout the whole motion, x component of the velocity equals to the initial component, initial x component of the velocity, x component of the initial velocity, right? So even over here. So y component 0, x component is initial, so essentially magnitude of the velocity at that point equals to the value of the x component of the velocity. Right? So what about time? So it's only 7:30, it's only 2 hours. Okay, so the last question probably. I prepared 2 additional problems, but of course I was not planning to solve it. All right, so you can look by yourself. So let's solve 1 additional question, and the rest you can look by yourself. Probably 10 minutes, 10-15 minutes, and we'll call it a day, because I can see you are kind of not prepared. Usually Physics 2 students are much stronger, so they usually stay throughout the exam review session. You know what, I will should be able to fit it. This problem is not as long as that one. So let me separate it like this. Engine. An automobile engine slows down from 3,500 RPM to 1,200 RPM in a given time, 2.5 seconds. And then we need to calculate something. Okay, let me, so it's a problem number 7. Let me get some water before I continue. So we have some engine. And you know, let me write it like this. So engine slows down. Let me write. And so initial omega naught equals to 3,500 RPM, revolutions per minute. Of course, you remember it. You're all engineers, so it's you use it a lot. And it slows down to, let's say, omega final, 1,200. So it's not stopping. It just slowed down. And in the period of time of 2.5 seconds. So, and it took delta t equals to, you know, let me, delta t, 2.5 seconds. 2.5 seconds. So that's what is given. And immediately we're going to make which assumption before we even start? Yeah, acceleration is constant. Deceleration, acceleration constant. We're going to make that assumption. It's a reasonable assumption, right? Although very often it doesn't work that way, but as the first level of approximation, why not? So now we need to, let me write, assume alpha is constant. Alpha, it's our angular acceleration. Angular acceleration, it's a dead quantity, alpha. So, and in part A, we need to find actually that angular acceleration. Yeah. So find alpha, which is again angular acceleration. Wait. Or maybe just in order to make clear, I can draw a graph, for example, omega versus time. So first, it was omega naught here somewhere. And then it decreased to this value, omega final. So this is TF, and this is T naught equals 0. Right. You remember, in all our kinematic equations, every time we assume that initial moment of time is 0. Right. We derive that way. I even don't feel like asking. Okay, suggestions in terms of equations. Which equation do we have to use in order to solve this problem? So these are kinematic equations. We need to find. No, actually, yeah. So which equation? The first one. Let's start analyzing. Final velocity is given. Initial is given. Acceleration we need to find. Do we know the travel time? Oh, yeah, it is. It's given. I thought there's no travel time. Yeah, okay, it's given. Yeah, so yes, you're absolutely right. That will be, of course, the easiest equation. I thought time is not given, so I thought about going to the last one. But yeah, it's correct. So omega f equals to omega naught plus alpha t. Yeah, let's call it tf. So it's a final. And so from here, alpha will be equal to omega f minus omega naught divided by tf. So, you know what? Okay, now start correcting. What we should have done before I started? Oh, yeah, he volunteered. So what? Yes. Now I started looking and I'm messing up, creating a big mess out of units. Our angular velocities are in RPM, revolutions per minute, right? And my time is in seconds. Again, it will be a big mess. It's an ugly mess. It's better to, you know what? Let me convert our angular velocities into the revolutions per second. At least in my notes, I decided to convert to revolutions per second. Let's spend this a little bit of time. Okay, let me stop here and convert. Which one I did first? Omega naught. Okay. 3,500 revolutions per minute, that RPM, right? And I want to get revolutions per second. Okay, so just getting rid of minutes is easy. 1 minute, 60 seconds. I just create a ratio which is 1. And of course, I want to get rid of minutes, so minutes must be upstairs, and seconds, of course, downstairs. So these minutes get cancelled, and we will get 58.33. And now it's revs per second. Right. And in a similar way, we can convert omega final. Omega final, so it will be equal to 12. Oh, let me write still. 1200 revs per minute. 1 minute, 60 seconds. Did I say 20? Yeah. 20 revolutions per second. Okay, so now we can go back and plug this number. So now everything will be fine. And the angular acceleration will be in revs per square second. That's normal. So it will be final 20 minus 58.33 revs per second and divided by 2.5 seconds. And of course, acceleration will be negative. Of course, negative, right? So it's decelerating, so it's negative. So minus 15.3 revs per square seconds. Right. So part B, the last question before we go. We need to find the number of revolutions between this moment and that moment. So to slow down from that angular velocity to this angular velocity, of course, it must turn over a certain number of revolutions. So let's find that. So now we need to find number of revolutions. Number of revolutions, of course, is just the angle. It's just a fancy way of calling the angle. Right? 1 revolution is 2 pi radians, 2 revolutions, 4 pi, and so on. Right? Pi over 2, it's a quarter of revolution. Right? So since travel time is given, we need to find angle, so it's equation number 2. Yeah, equation number 2. So you see, it's like with these kinematic equations, except for now we just convert everything to the angular quantities. Theta final equals theta naught plus omega naught t final and plus 1/2 alpha t final squared. Omega naught is 0. It makes sense to make an assumption to start measuring angle from the initial moment of time. So theta naught is 0. Right. And yeah, omega naught is given. Final time, travel time we have, and yeah, so just plug and calculate numbers. Okay, let me plug the numbers. So omega naught 58.33. I will skip units. Travel time 2.5. Alpha, where is my, we found alpha, it's this. So minus 15.3 and times 2.5 seconds squared. Okay, so 97.9 revolutions, essentially 98 revolutions. So you see this type of problems even slightly, even more straightforward because we have only one direction. You don't have to play it with x and y motion separately. Right. But still, based on my experience from the past, still plenty of students are not very comfortable with this angular velocity, angular acceleration, but it's very, very similar to this. Ideologically, of course, slightly different. Okay, so enough.